Welcome. Hey, my name is SmartMe. And what we do is to try and simplify the process which we are able to handle to give you the best chance that you have got as that grade 12 for exam. The more concept, this is what we are introducing today, or this is what we are handling today, the more. And I think this lesson is applicable for guys in grade 11 and grade 12. I think the guys in grade 10 it will be a little bit too far because they have something still to cover. Or if you do inform, this will be in either for 3 and for 4 because this is where your examinations comes maybe in the next 1 year for grade 12 and for 4 the next 1 year or within this year, you are going to sit for it, meaning that you don't have much time. Grade 11 and grade and form 3, you still have some time, so it means that you saw this one early. So, welcome. If you haven't watched a certain introductory video, I highly recommend that you go and have a review of that because it's going to guide you how you are going to be using these particular videos and how to best optimize your chance of understanding everything, as well as some basic mathematical principles which we expect you to know and which we'll be using in here. All right, so let's get right into it. The more it goes like this. Let's let me tell you like this. uh when physics or physicists or people out there, they are measuring, let's say even if it's in the shop here to you, we know that when you go to buy 1 kg of let's say sugar, it will always be 1 kg, right? Because this 1 kg, there is a mass which is saved somewhere. I don't know in the which institution somewhere in London, that they have a block which measures 1 kg, and this is the standard. They say if you have a doubt with your kg, you think it is smaller or it's not measuring so properly, this is you come and compare it to this. Of course, it's not accessible, but there is such a thing. Uh, there is also you know, 1 meter. Like the size of the ruler for your teacher. There's also a length which has been measured and cut and put somewhere, like a souvenir or in some museum somewhere, and it is told is a standard length of 1 meter. If you have a doubt between the 1 meter which is being shared with you or measured for you by someone, you need to compare it with this 1 meter to know that it is the meter you are being told is neither too big nor too small. Okay, this kind of arrangement, they are called standard international standard units or SI units. And this how come we say that the SI unit for length is a meter. The SI unit for kg is a kilogram, right? It is the standardized unit against which we measure this particular quantities. By quantities, I mean kgs and kg measures the mass, and measures the meters or measures the length. Now, when we know that when we are dealing with the chemistry and chemical reactions, the best what we are dealing with is reactions or the behavior of atoms. Behavior of atoms. Okay. Now, but now the problem is that the atom is too small. The atom is too small. Now, if we start trying to make calculations and we are basing them on individual atoms, our life will be too difficult for us to achieve this. So we need a way to standardize a number of atoms grouped together so that we can, I tell someone I'm dealing with this number of atoms, and he tells me he is dealing with a certain number of atoms, there is a relative thing against which we can all agree. Okay, and what was chosen was that thing or animal, not animal really, called the mole. It is now said to be the SI unit of the chemical reactions or measuring atoms which are taking place in a certain chemical reaction. Okay, I too much for that introduction. Let's go a little bit back. Let's go a little bit back. Let's take an element like or any element before we even get there. Let's start with the basics. You are told about atomic number. Atomic number. Atomic number, and that periodic table. And by the way, you needed to know the first 20 element, number 1 to number 20, by heart, especially the atomic numbers. The atomic numbers. Whenever I tell you about the atomic numbers, you realize a number of things from that atomic number. One, you realize the number of protons or positive charge in the nucleus of that element. How is the element looking like? Let me start with something simple like I'll go with which one? Let me go with sodium. Sodium. Okay. If I tell you that sodium is number 11 on the periodic table, or I tell you that its atomic number is 11, what I'm telling you that is that this sodium, he has 11 protons on his nucleus. So this is our sodium. He has 11 protons, and protons are positive charge. That's what it is implying. It's implying there. Number two, that we know whenever an atom hasn't taken part in a reaction, it's chemically neutral. If it is chemically neutral or electronically neutral, it has some electrons to cancel out its those positive charge with the proton. So this tells me that if sodium has 11 protons, or if its atomic number is 11, first of all, we know that it has 11 protons, as we have said. Now we are saying by default it must have 11 electrons hovering around its structure in a certain way. So those 11 are usually distributed 2, 8, 1, so that you have 2 there, you have some 8 here. I think this is how you used to draw them. And you have the last one there. Okay, that's that's what you know from atomic number, the second thing. And number 3, when I tell you that the atomic number of sodium is 11, you know that it must be number 11 on periodic table. You know its position on the periodic table. So I know that sodium must be number 11 on the periodic table. I made sure that I put this periodic table near here. And if I go to sodium there, you can see 11 there. It is, you count, it will be 1, 2, helium 3, 4, 5, 6, 7, 8, 9, 10, and it is number 11 over there on the periodic table. Okay, I go like that, you can see the implication in there. So those are the first 3 things you know. Now, that's well, by the fact that I'm being told that the atomic number of this element is 17. So the atomic number of this element is 17. Yeah, 17. I'll know that this guy, he has 17 protons on his nucleus. He has 17 electrons on his energy levels, and he must be number 17 on the periodic table. This is actually correct, right? That's the first thing we know when we know about the atomic number. Now, the next thing which we should be aware about is something called the atomic mass. And the atomic mass of an element always or of an atom will be equal to the number of protons, plus the number of neutrons. Neutrons, they carry no charge, and they also stay in the nucleus. So if it is sodium, it's well known that it has 12 neutrons, and therefore for our sodium there, if we know he has 11 electrons and 11 protons and 12 neutrons, it means that his mass number must be 23. And this 23 is, you see sodium written as sodium 23 as superscript there and 11 like that. This number here is the atomic number. That number here is the mass number. All right. So then a little bit more forward, this mass number, once you have it, we get a little concept of relative atomic mass. The relative atomic mass is the atomic mass of a substance, atomic mass of a substance or of an atom divided by 1/12 of a carbon atom. Now, carbon, its mass number is 12. All right. So if we divide the mass of atomic mass of carbon by 12, you essentially get 1. Because what scientists did was to agree that let's agree without basing any whatever, or after this chemical reaction we have done, after knowing this carbon so well, let's decide that this carbon 12 atom, it's actually a special one. They call it carbon 12 because carbon is a radioactive. It can become radioactive, so it can have different masses. But let's take as carbon 12 as our standardization unit. Take 1/12 of it. Say that is the atomic mass unit we are going to be using. 1/12 of that one. 1/12 of atom. What I'm saying, 1/12 of carbon is what is called the atomic mass unit, the smallest unit that we can use to classify. So when I say that sodium is mass number is 23, I'm saying it is 23 times heavier than 1/12 of an atom of carbon. But you don't need to know all that because most of the time the atomic mass will be given to you, will be handed over to you. I hope you are taking note. This is necessary. Chemistry, mathematics, physics, and any other subject which has a lot of calculations. You need to be doing practical. Don't let your brain cheat you to take shortcut. There is no shortcut. It's all about the exercises. So make sure you're taking notes and you are getting busy so that you don't get bored. Now, so we know about the atomic mass and the relative atomic mass. So what will happen is that you see on the periodic table, or even in the exam, you'll be told that if you take an atom like nitrogen, it's number 7, meaning it's number 7 in the periodic table, meaning it has 7 protons, meaning it has 7 electrons, and then you are told it has a relative atomic mass of 14. So whatever is indicated on the periodic table there, those are relative atomic masses of those particular elements. Now we come to the real deal. When chemists did a lot of research and lots of calculation, they realized something. If you take a certain mass of sodium, let's say take, for example, sodium, which I know is, I said I write it like 3. This is its a relative atomic mass, which I know is a relative atomic mass is 23. And I take 23 grams, which is equivalent of its relative atomic mass. I count the number of atoms there. I find that it has those number of atoms of sodium. If I took another element, let's say, sorry, another element such as aluminium, and its relative atomic mass is 27, and I take 27 grams of aluminium, I'll find and count the number of atoms in there. I'll find it has those number of atoms of aluminium. If I take another element, let's say like lead, whose relative atomic mass is 207. By the way, relative atomic mass doesn't have doesn't have units, because we said it's a ratio, it's a division of 2 units, so it doesn't have. So this quantity here, I leave it without grams because it is RAM, relative atomic mass. It has no grams, it has no units. So I'm saying I know that the relative atomic mass of lead is 207. But then I go and measure now 207 grams of lead, and then I count the number of atoms inside there. I'll find, or again, it is equal to the number of atoms in there of lead, they are equal to that atoms of lead. So then they came to come and a conclusion that we will define as 1 mole of any substance will be that quantity of mass, quantity of substance, which when you count the number of atoms of that substance or particles of that substance at that particular moment, you should always get that number. And this number is called the Avogadro's constant. And the implication is that 1 mole of any substance will always contain 6.0 times 10 to power 23, right? And then what's that other implication? They realized that if you take the relative atomic mass of a substance, especially let's say of sodium, aluminum, calcium. If you take the number of grams which are equivalent to its relative atomic mass, then you calculate the number of atoms inside, they give you that Avogadro's constant, and which implies that for most of these substances you find on the periodic table, their relative atomic mass also gives you the weight, the mass of 1 mole of that substance. I hope that is too much. And what I mean as of now is this, that 23 grams of sodium is equals to 1 mole of sodium. 27 grams of aluminium is equals to 1 mole of aluminium. 207 grams of lead is equals to 1 mole of lead. I will go to the periodic table and pick a random atom. I don't know it is iridium, this atom, or this is platinum, PT. It's 195. So 195, platinum is PT. I will come here and say that if I take, I don't need to know it, I take 195 grams of platinum PT is equals to 1 mole of platinum. And if I go inside here, I try and count the number of atoms inside this 23 grams, I'll find is equals to that number. If I find I take 27 grams of aluminium, I go inside and count the number of particles which are there, I'll find the same number. The same, I come here, I take 195 grams of platinum, I count the number of atoms of platinum inside, I'll find that particular number over there. All right. So once you know that, now how are they going to be pushing the questions to you? They will come and ask you that how many, if I have like, let's say like a 2 times 10 to power 23. Sorry, I need to make it better. Sorry about that. So I'm saying this is what we are going to be saying. The question will be like, how many moles of aluminium have 2.0 times 10 to power 23 atoms of aluminium. Okay, so I'll come here and say, remember what I said, that I know 1 mole of aluminium must contain 6.0 times 10 to power 23 atoms of aluminium. So how many moles contains 2.0 times 10 to power 23? So I cross multiply, don't get confused. Yeah, I get 1 mole multiplied by 2.0 times 10 to power 23 is equals to x multiplied by 6.0 times 10 to power 23. I want to make x the subject of the formula, is to divide both sides by that amount. To divide that, the other side, whatever you do on the left hand side, do it on the right hand side. So that one goes. So I come here, I divide that 3 that goes. So I'm left with x is equals to 1 over 3, which is equals to 0.33 mole. Okay, those are the number of moles which will contain 2.0 times 10 to power 23, right? Another question, how will it be asked? Another the question will be like asked like how um, how many atoms are there, atoms in 2 moles of sodium. I'll come here and say that 1 mole of sodium, it has 6.0 times 10 to power 23 atoms of sodium. So 2 moles of sodium, how many atoms are there? I do cross multiplication. You get familiar with this and make sure you're following up with you. Do actually doing this exercise and don't just look at it, write it down. That's the way you are going to get familiar with it, and you get to do this calculation. So cross multiplying, I'll get that x, you see this is 1 mole. I'll be, for now, we do those 2 steps so that you can follow. Later on, I'll stop adding some of the unnecessary component. Here, I divide by 1 mole, divide by 1 mole. I want you to see the mole going. Okay, so I'm left with 12 times 10 to the power 23. This is 23. Okay, I can't leave it like this. This is the same as 1.2 times 10 to power 1 times 10 to power 23. These two indices, 1.2 times 10 is 12, because this moves decimal place to the forward. This one becomes 12. So this is okay. So these indices are the same base. I added the powers, so this one becomes equals to 1.2 times 10 to power 24. I talked a bit about this one in the introductory video. That's why I was saying, if you haven't seen it, take a moment and go ahead and review it. Okay, everyone is okay up to so far so good. One more example. How many atoms of carbon are in 1.45 moles of carbon? How many atoms of carbons, I'm sorry, atoms of carbon in 1. Make it a little bit better, 0.15 mole of carbon. Okay, so I come here and say that 1 mole of carbon, I know it must have 6.0 times 10 to the power 23 atoms of carbon. So if I'm dealing with a 0.15 mole of carbon, how many atoms must they have? I do cross multiplication like that, and here you get x becomes 6 multiplied by 0.15 multiplied by 10 to the power 23. I multiply this one, this is 90. 15 times 6 is 90. Okay, and then two decimal places. Anytime when you are multiplying a number with a decimal, don't get whatever. If I'm told you to multiply 6 multiplied by 0.15, I first of all avoid the decimal. I multiply 16 by times 15. I get the answer is 90. Then I needed to introduce the two decimal places. So the decimal is there in it's 90.0. You two decimal places to the left, 1, 2. So I am getting 0.9 times 10 to power 23. So I can't leave it like this. It doesn't look good. This is the same as 9.0 times 10 to power minus 1. Power minus 1 is the same as saying 0.9. Look at this. 0.9 is the same as 9 over 10. Okay, so if I need to remove this 10 from the bottom, it's the same as saying 9 multiplied by 10 to power minus 1, because 1 over 10 is the same as 10 to power minus 1. This one means 1 over 1 over 10. I hope that's about indices. You might need to review that one. The reason I keep saying this is because if you have some weakness with this mathematics of indices and stuff like this, you may know what you need to do in the chemical part of the equation, but then the mathematics fails you. So at the end of the day, you fail. So we need to avoid that. So go back and revise some indices and logarithm. Okay, 23, and then what happens when you are adding, when you are multiplying items with bases which are the same, you add the powers. So this is 10 times 10 to the power 22. I said in the introductory video, if you are adding two numbers, minus 1 plus 23, you are adding them. Two numbers with different signs, subtract them and put the sign on the bigger number. Then the bigger number had a positive. So you subtract them, you put tag 22, and it is a positive like that. Okay, so and this is what we are left with, that it is 9.0 times 10 to the power 22 atoms of carbon. I think with that one, you are ready to go back to your textbooks and hammer up all the exercises which are there. Don't get tired. Don't get tired. The better you discipline yourself to avoid getting tired, the better your chances are at being able to achieve this one. The more exercises you do, the more guaranteed you are, or the closer you are to being guaranteed of success. You remember a step back there, what did we say? We said, remembering what we said that I know 1 mole of sodium must weigh 23 grams and must contain 6.0 times 10 to the power 23. I said, let's say 1 mole of aluminium must weigh 27 grams and it will always have the same number of particles. We said something like 1 mole of something like calcium is equal to 40 grams and must contain 6.0 times 10 to the power 23 grams. The mass of an atom, the mass of atoms which contains the Avogadro's number of atoms is called the molar mass of a substance, and which we said we know corresponds to the atom's relative atomic mass now in grams. Right. So whenever we talk of molar mass, we are talking of a quantity of a substance which contains 6.0 times 10 to the power 23, and which we are in luck because we know it always it's always equivalent to its relative atomic mass. So then when we know that, what are they going to be asking us in those kind of equations? We'll be asked to find how many grams are there in 44 grams of lead. Or let's not first of all start with the grams. Let's start with the moles. So we say how many moles are in 44 grams of lead, of not 44 about, but 414. Okay, let me pick a different pen. Grams grams or mass of lead Pb is 414. How many moles? Okay, so what are we going to do here? We are going to say that I know 1 mole of lead. If it is true, and of course it is true, I know that 1 mole of lead is 207 grams, which is its relative atomic mass. So how many moles are in 414 grams? So again, I do cross multiplication. I said I don't need you to remember or to memorize that this is the formula for calculating moles. I just need you to be able to see the relationship. Once you know the relationship, the formula for calculating the mole will bring itself. And what do I mean? That I'm saying that 1 mole of my lead is equal to the mass which contains its Avogadro's number, which happens to be its relative atomic mass in grams, which is 207 in grams. So we do some cross multiplication. We are going to get 1 mole times 44 grams, 414 grams is equals to 207 grams multiplied by x. I divide by 207 grams because I'm in the process of making x the subject of the formula. I divide the other side by the same 207. So I cut those ones out, they cancel out. Grams and grams on the right hand side cancel by 2071 by 2072. I'm using this beta, whatever, the answer becomes 2 moles is equals to x. This tells me that if I have 214 grams, that is equivalent to 2 moles of lead. And this is allowed, shortened like that, it's able to be accepted, all right? Okay, I was saying that I'm using some simple, whatever, simple ratios to avoid the complicating. But when you go to your exam, you might get some more complicated, not very complicated, or more smaller or bigger quantities. So you would have to deal with it as such. Like the other time, instead of asking that, I will ask something like atoms in, find atoms in 4.14 grams of lead. Okay, so what do I know? I know this that 1 mole of lead must be equal to 207 grams and must contain 6.0 times 10 to the power 23 atoms of lead. Now, we want to know the number of atoms in 4.14 grams of lead. How many atoms are there? Write terms together, 207 and 4.14 grams on one side, the Avogadro's number and the X on the other side, because we are looking for the number of atoms. I do cross multiplication. We'll be doing this one for a long time, for many times. And you find this one gives us 207 grams multiplied by x is equals to 4.14 grams multiplied by 6.0 times 10 to the power 23. I divide by 207 on the left hand side. I divide 207 7 grams on the right hand side. So the left hand side, this one goes, and I'm left with the gram and gram go. This one becomes, I said, if you want to divide a number with the decimal, first of all, assume the decimal, pretend the decimals are not there, do the division, then you introduce the decimal. So 414 divided by 207, I'm going to get, by the way, before I do that, that one right there is the formula for calculating moles. Mass you are given over the relative atomic mass in grams. That's the mole there. That's why I said you don't need to remember the formula. The moment you substitute or correctly, the formula will show itself in there. You don't need to remember it. So I'm saying we are dividing 4.14 divided by 0207. Arithmetic Assume the decimals are not there, do the division, the answer is 2. Then introduce the decimal, it is two decimal places. In any number you write it, the decimal is there, it is 2.0, but we never write 0.0 because the 0 is insignificant. So we come here, introduce two decimal, we do 1, 2. So the answer becomes 0.02 times 6.0 times 10 to power 23. Now we can't live like this. This number is the same as 2 times 10 to power minus 2. Remember that behind there, I said this is the same 0.02 is equal to 2 over 100. Get familiar with this mathematics because they will mess you. So, and I said that this is the same as 2 times 10 to the power minus 2. If you don't know this one, sir, the mathematics will always confuse you and this one will give you an issue. So then what happens? This one becomes 12 times 10 to the power minus 22 minus 2 times 10 to the power minus 23. We are not yet done because the 12, we cannot leave it like that. The 12 is the same as 1.2 times 10 to the power 1 times 10 to the power minus 2 times 10 to the power 23. So these bases are the same. We add the tops. This is a 1 minus 2 minus plus 23. The same as 24 minus 2. It will become 1.2 times 10 to the power 22. Okay, atoms of lead. Of course, you see, majority of, especially like this one, majority of the part was the mathematical part of it. So that's why I need you guys to be very, very familiar in how to handle this kind of mathematics. Okay, yeah, you can go back and check that one until you are very okay with it. How many moles are there in 54 grams of aluminium? I have 54 grams of aluminium. How many moles? I will say that I know 27 grams of aluminium is equivalent to 1 mole. Okay, because I know that aluminium is 27. I go back to my periodic table. Aluminium is right there. You see 26.98. This one is usually approximated to 27. So I know 27 grams of aluminium is 1 mole of aluminium. So what about 54 grams of aluminium is equals to how many moles? I cross multiply again. This one will give me 27x is equals to 54. I divide by 27. I divide by 27. I'm avoiding writing the moles and the grams. This one will give me 2 mole. I know the answer I'm expecting is the moles. Make sure that when substituting, you do the correct substitution. Okay. Another one. What is the mass of 0.05 mole of sodium? That I'm told that I have 0.05 mole of sodium. And then I must, what is the mass or the weight, not the weight, but the mass is the grams that I'm expecting. What do I know? I know that from our past, we know 1 mole of sodium is equal to 23 grams. Okay, what about 0.05 mole? Of sodium is equals to how many grams? So again, substituting correctly, 1 mole of sodium is 23 grams. But even if you say it the other way, it will still work out. It doesn't matter the way you put it, so long as you put it correctly. 1 mole of sodium is equals to 23 grams. 0.05 mole of sodium is equals to how many grams? If you get confused with this one, I can still do it the way I did the other one. I say that 23 grams of sodium is equals to 1 mole. What about how many grams is what? 0.05 moles. Whichever way you put it, you end up with it at the same point. So whether I use the first or the second substitution, I get the same. So using the second substitution, I can do cross multiplication like that, and I'll get that 23 will be multiplied by 0.05 is equals to x. All right. x of course times 1. This one is telling me that whenever you have a mass, whenever you have the moles, to get the mass, you multiply by the molar mass by the moles you have been given. This is a formula which the textbook will say you need to know. But what I'm saying is that you don't need to know it, because when you substitute correctly, the formula will come by itself. And I'm going to get here that my number of grams is equals to 23 is a 15, carry 1, 10, 11, 115. I said when you are multiplying quantities or dividing quantities with the decimals, avoid the decimal, do the multiplication, then introduce the decimal. So two decimal places, 1, 2, and this will give me 1.15 grams of sodium, equivalent to 0.05 moles of sodium. Okay. I don't know what else that can be asked there which can give you a problem. So again, I request you to go back to your textbook and try and find out what I mean, attempt all those questions which are in there. There must be a lot of questions. How many moles in 11.5 grams, 11.5 grams of sodium? So I'll come here, I say I know that 1 mole of sodium is equals to 23 grams. What about how many moles are in 11.5 grams? As you can see, always write terms together, grams, moles. Here I know it will be x moles. So I cross multiply, and I'll get 11.5 multiplied by 1 is equals to x multiplied by 23. I divide by 23. I divide by 23, and that one will go, so that my x will become what? What is this number? Can I, one, do long division, 115 divided by 23. 23, how many times does it go into 15? Is actually 5 times. Is 5 times, I get 115, and it is finished. Then introduce 1 decimal point, it will become 0.5 more. And that is your answer right there. Okay. Okay, so arithmetic here. I saw something which you can benefit. Arithmetic here. If I'm going to divide this 115 is the same as 115 divided by 23 times 10. This 10, I brought it down because if 115 divided by 10 is 11.5. Okay, so I divide this one, I get the answer becomes 5 over 10, and this is the 0.5 in answer. Then not important, but it might help you somewhere else. Okay, so we have dealt enough. I think those are enough exercises to deal with the moles of simple atoms. Okay. Didn't intend to save that one. I intended to do a new one without saving. Okay. Right now, let's now consider something. It's in the same we are in the same category, but now we make it a little bit not complex, but a little bit a step forward. How are we going to do? Consider molecules or like something like oxygen, O2 as an guys, nitrogen, something like carbon dioxide, something like water molecule. Of course, these molecules, they are made up of atoms, so of certain elements. So O2 means it is two oxygen atoms combined together. N2 means it is two nitrogen carbons and two nitrogen atoms combined together. H2O means it is two atoms of hydrogen combined with one atom of oxygen. You remember just something out of the more concept a bit, just to so that we can also breathe. Oxygen, we know oxygen is number 8 in the periodic table, so it is in that 26 in that configuration for its electron. So how is the oxygen molecule formed? The oxygen molecules will be formed like you have the first energy level has two elements like that. Then the second level has 6. 1, 2, 3, 4, 5, 6. Okay, so this oxygen, for it to feel nice, it needs to have some 2 on its outermost energy level so that it can be stable. It can't be able to stay on its own, so it has to get another oxygen atom near it like that. Then they share some 2 electrons like so of on the outermost energy level. So when this black dotted, I should have used a different color. The dotted carbon is counting his electrons. Oh, not carbon. Excuse me. Anytime you make sure you are following up, don't get confused when I am saying the wrong thing. When this one is atom B, if this atom A is counting his electron on the outermost energy level, it's going to count 1, 2, 3, 4, 5, 6, but also count the neighbor 7, 8. Same with this guy, he will count 1, 2, 3, 4, 5, 6, and also count the neighbor 7, 8. And it feels like it has reacted, and therefore it is stable. That's how an oxygen molecule is formed. And it's the same truth here. If I try to draw for you the water molecule, it will be the same oxygen like that. Oxygen. Let me do so. Then 1, 2, 3, 4. Then one there and another one there. I'm bringing because another one there because I'm putting hydrogen here. Hydrogen is usually atomic number 1. So it has only 1 electron, which is that one there. And the same with this guy on the other side. It has only 1 electron right there. Okay, and that one there becomes your water molecule because that is hydrogen and the oxygen there. So for this element, you can see now the structure, how it is looking. So when we consider the relative or atomic mass of oxygen, molecules because oxygen, you will never find oxygen atoms staying and it's floating about. The air around you is oxygen molecules. So when we say we are breathing oxygen, we don't mean oxygen atoms, we mean oxygen molecules because you don't find oxygen atoms anywhere alone. They need to be combined with another one to form that oxygen molecule. So what are we saying? That when we consider the masses of this, or when we are calculating the moles of this compound, because essentially they are now compounds, you see this is the covalent bond, and for you to break it, you need some energy, you need to push in either heat onto that environment or some pressure. For that to happen, so they are essentially compounds. When we are considering their formula and their masses, now you see we will be saying the mass of oxygen is now equivalent to 2 oxygen atoms, 2 multiplied by 16 from our periodic table here. You see that oxygen has 15.999, which is equivalent to 16. So the mass of oxygen atom is equal to 32 grams. The mass of oxygen molecule is equal to 32 grams. The mass of nitrogen molecule is equal to, because the nitrogen itself, the nitrogen atom is 14 grams, the molecule of nitrogen is by 14 by 2, which gives 28 grams. The mass of carbon dioxide will be equal to one mass of 1 carbon, which is 12, multiplied by 2 oxygens, which will be 32 plus 12, which comes to like 44 grams. The mass of a water molecule will be 2 hydrogen, which is 2 multiplied by 1 because 2 hydrogens and each hydrogen has a mass of 1 plus 1 oxygen, which is 16, which becomes 18 grams. And now we have what we call the relative molecular mass. And the relative molecular mass here, we are talking of the mole or the mass of one atom of or one molecule of compound of a compound, in this case molecule of a gas. And then these molecular masses now they become their molar mass. Okay, so we are saying now on the other hand, at least I can take out this one. I believe people have seen it. I always need you to see it so that you are able to more understand it. Okay, so what I'm saying is this, that I pick a green, 1 mole of oxygen gas, oxygen molecules, oxygen gas will be equal to 32 grams and will contain 6.0 times 10 to power 23. Remember what we said previously, but this time molecules of O2. I will say that 1 mole of nitrogen gas its weight will be 28 grams, and this amount will contain 6.0 times 10 to power 23 molecules of nitrogen gas. I come to 1 mole of carbon dioxide will be weighing 44 grams and will contain 6.0 times 10 to the power 23 molecules of carbon dioxide gas. All right. I will say that 1 mole of water molecules will weigh 18 grams and will contain 6.0 times 10 to the power 23 molecules of water. All right. So that is the implication. Now, you remember previously when we were dealing with the sodium, we were saying 6.0 times 10 to the power 23 atoms of sodium. Now we are saying 6.0 times 10 to the power 23. Where's my pen? Where's my pen? Come closer. Molecules of oxygen. What does this mean? Why do I have to be a little bit careful here? Is because when I say 6.0 times 10 to the power 23 molecules of oxygen, you realize that each molecule of oxygen has 2 oxygen atoms. 1 molecule of oxygen, if I take one O2, number 1, I'll say, let me say, if I take three molecules of oxygen, they have 6 oxygen atoms, O atoms. Okay, why? Because 1 atom has 2 atoms of oxygen, then another one has 2, then another one has 2. So if I calculate, you remember this is the structural, the way I had drawn them. Sorry, they look like eyes, but it doesn't matter. It's an oxygen, an oxygen, an oxygen, an oxygen, an oxygen, an oxygen. So if I am dealing with 1, 2, 3 molecules, the total number of oxygen atoms is 6 oxygen atoms in three molecules of oxygen. So when I deal with the 6.0 times 10 to the power 23 molecules of oxygen, you see it will contain here 2 multiplied by 6.0 times 10 to the power 23 atoms of O. Okay. But before we confuse ourselves and shoot ourselves in the leg, remembering this portion right there, remembering this portion, where's my pen? Remembering this, yes. Okay, let's first of all look at how they are going to give you some of the exams, the exam equivalent questions. Okay. A mass of 3 moles of oxygen gas. What is the mass? Mass of 3 moles of O2 gas. O2 gas. So I'll say I know that 1 mole of oxygen gas is equals to is it 32 grams? Okay. How? Because I know that the oxygen has an RAM of 16, so it is 16 grams, but one oxygen molecule, excuse me, is equal to, has 2 atoms of oxygen, so it is 16 times 2. This 32 is from 16 times 2. So what about 3 moles of oxygen gas? How heavy is it? I do the cross multiplication again, and I will get my x is equals to 3 multiplied by that 2 grams, which will give me 96 grams, right? Pretty easy with that one. Another one, moles contained in 14 grams of nitrogen gas. Moles in 14 grams of nitrogen gas. All right. I know, what do I know? That 1 mole of nitrogen gas must be 28 grams. Why? Because if N2 has 2 atoms of nitrogen, and 1 atom of nitrogen is 14 in terms of relative atomic mass, then N2 must be 14, 28 grams. So how many moles X are in 14 grams? Okay. Okay, I know that one is a bit confusing, but make sure you revise what we have just talked about. You should be able to see it. So if this is the case, I do the cross multiplication again, and then I will get that 14 is equals to x multiplied by 28, divide by 28 this side, divide by 28 that side. I'm making the x the subject of the formula. So I'll find x is equals to 1 over 2, which is equals to 0.05. This is by 14 1 by 14 2, 1 over 2, which is 0. Not 0.05. One of the 0 is not there. Sorry, this will be there. A half is 0.5. Okay, so it's which is 0.5 mole of O2, and not O, but N2, nitrogen gas. All right. Calculate the mass of 11 grams, no, moles of in 11 grams of carbon dioxide gas, moles in, they say we have 11 grams of nitrogen gas, carbon dioxide gas, 11 grams of CO2. How many moles? And this one, we said it is C, which is 12 plus 2 oxygens, 16 multiplied by 2. So this one gives 12 plus 32, which is equals to 44. So I'll say that 1 mole of carbon dioxide is equals to 44 grams. How many moles are in 11 grams? I cross multiply, and I'm getting 11 is equals to 411, and here we have 1 mole. Okay, is equals to x multiplied by 44 gram, divide by 44g, divide by 44g, and then that one comes, so that our x we are being left is equals to 11 over 44 moles by 11 1 by 11 4, and the, by 11 4, and then this one will get that our x is equals to 0.25, or a quarter of a mole. Small arithmetic, a quarter is 0.25. If you are not sure, I think you can leave it as a quarter, but I won't recommend. But if you find a fraction which you are not able to divide, but I believe maybe you'll be given some calculator you might be allowed, you might not, or logarithm table use it for the long division, but that is arithmetic. I told you, make sure those small arithmetics don't mess you up. Make sure that those small arithmetics they don't mess you up. All right. We try another one. The mass which is contained in 0.35 moles of oxygen. Let's start with that one. It's saying what is the mass of 0.35 0.35 mole of oxygen gas. What's the mass? Find the mass. And mass, of course, it will be in gram. So what do I do? I know that 1 mole of oxygen gas is equals to 32 grams, 16 by 2, or you remember the relative of molecular mass. What about 0.35 mole is equals to what? I cross multiply with my x, and I will get the action is equals to that 2 into 0.35. As I said before, when you are multiplying 2 units and one has a decimal, ignore the decimal, do the multiplication, introduce the decimal. 32 by 5 by 35 is this one here, multiply 0.75 carry 1 75. Is that right? No, it's not. 5 carry 1 9 10. Add them 12 carry 1 1 and 1. All right, then 2 decimal places 11, so that becomes 11.2 grams. And make sure it makes sense if I'm dealing with if I know that 1 mole is that 2 grams, 0. Whatever 0.035 is smaller than 1 mole, I should get less number of grams. You should the answer should of course make sense to you, so that you know that you are not wrong somewhere. Okay. Here is an interesting one. It's an interesting one. Assuming that the air is 20% oxygen. No, that is not the one. That is not the one. This is saying that it's a real application that this bucket, you have one bucket of water, which is 20 kg. Your regular bucket, you know it. That bucket where you store water is 20 kg in weight. Okay, how many moles of water are here? Moles of water. This is a real life one. Moles of water in this bucket, okay, or jerrycan, or whatever it is that you want to call it. Okay, so what mass am I dealing with? Remember, if we are going to do good molar calculation, our mass must be in grams. So 20 kg is the same as 20,000 grams. One kg is equals to 1 kg is usually 1,000 grams. This one you needed to know. Is I need to know. I think you are required to know that one. So 20 kg is equals to 20,000 grams. So water, what's the mass of 1 mole of water? Is 2 plus 16. This 2 is 2 multiplied by 1 because 1 hydrogen has an RIM of 1, and therefore 1 mole of hydrogen is 1 gram. So I'll get 18 grams. So what happens is that I'll say 1 mole of water is 18 grams. If I have 20,000 grams, how many moles are there? I cross multiply that, and then I'll get my 20,000 G multiplied by 1 mole is equals to X multiplied by 18 gram. I divide by 18 gram. I divide by 18 gram. Gram and gram goes. So I'm left with this one by 2, 9 by 2, 10,000. Okay, so X is equals to, allow me to take my calculator right now. I hope you'll be allowed to have your calculator with you. 10,000, 10, 1, 2, 3 divided by 9 is about 1,111. It's 1,101.1 moles of water. Okay, so I think so far so good. So far so good. So far so good. And now we come to the other side of particles, considering the same, because we already said, what did we say? We said that if I have 1 mole of, let's say, oxygen gas, I know that this one is that 2 grams. If it is really 1 mole of oxygen gas, it must contain 6.0 times 10 to the power 23 molecules of oxygen, molecules of O2. It goes without saying, if it is a mole, it must contain that number of those particles you are dealing with, in our case, O2 molecules. So if I'm asked how many atoms are in if I'm asked how many atoms are in 15 grams of mm, 8 grams of oxygen gas, O2 gas, how many atoms are there? I'll come and say 1 mole of oxygen, I know is equals to that 2 grams. It has 6.0 times 10 to the power 23 atoms. If I have 8 grams, how many atoms are there? I do some cross multiplication like that. I'll get that 2 multiplied by x is equals to 8 multiplied by 6 multiplied by 10 to power 23. I divide by that 2. I divide by that 2. And then by 8, 1 by 8 is 4. 6 over 4, I can divide by 2. 2 by 2, 3. 3 over 2 is the same as 1.5 times 10 to the power 23 molecules of O2. All right. Okay. If someone asks me something like, what's the mass, or what is the number of particles in 3.5 grams, 3.5 grams of nitrogen gas, I'll come here and say, I know that 1 mole of I'm calculating the number of atoms or number of molecules of N2 in this mass. So I will come and say 1 mole of sodium is equals to 28 grams and must contain 6.0 times 10 to the power 23 molecules of N2. So what about 3.5 grams? Will contain how many molecules of N2, and cross multiplying like that, we get 28x is equals to 3.5 times 6.0 times 10 to the power 23. I divide by 28, I divide by 28, so that I'm going to get, I can divide by 7, by 7, 4, by 7 here, I said you divide, you get it is 5, then you introduce the decimal, then we can multiply this one, we'll get 30. Let's do it here on the side. 30 divided by 4. What is that divided by 4? By 2, 2 by 2, 15. Okay, 15. And then 15. So what's not right? What's not right? Oh, yeah, no, it's right. 15. This one I divide by 1. I This is not 30. Oh, that's what is the problem. That this times this is not 30. It's 3. Because 6 times 5, 6 times 5 is 30. Then you remove one decimal place, it becomes 3. So the answer should be really 3 divided by 4. And 3 divided by 4 is equals to 0.75. 0.75 times 10 to the power 23. Then this is the same as 7.5 times 10 to the power minus 1 times 10 to the power 23. And this is 7.5 times 10 to the power 22. We said that when the bases are the same, add the powers. And if we are adding minus 1 plus 23, subtract them and put the sign on the bigger number. The bigger number was 23. So the answer becomes that these are atoms, are not molecules of N. Why does it feel not okay? It doesn't feel. Oh yeah, no, it's fine. It's actually very fine. I was not aware this is part 22. I was trying to wonder why does it feel like it is bigger than the original number 6.0, and yet we are using a smaller mass. But this number part 22 is very, very much smaller than the other one. Okay, and with this one, I don't know what else which can be asked, which is trickier than that. What's the weight of how many moles are in 6.5 grams of carbon? We find the number of moles and the number of molecules of carbon in that one. We are looking at the 6.5 grams, 5 grams of carbon dioxide. We find moles and number of atoms. Yeah, by the way, you don't abbreviate like this. So we are saying, I know that 1 mole of carbon dioxide is equals to 44 grams. How do I know it is 44? Carbon 12 plus 2 oxygens, 32, which is 44. 32 is 16 multiplied by 2. Okay, so what about 6.5 grams? Maybe this one looks familiar. We have done it. And then we are going to get that x multiplied by 44 is equals to 6.5 grams multiplied by, this is gram, multiplied by 1 mole. So divide by 44, divide by 44. I get this one will be coming to what? What can we divide these two numbers? Or I can just use my calculator. 6.5, quickly 6.5 over 44 is a point. The answer here becomes z. Am I having the same correct? Yeah, brush I do 0.14148. I have appropriated to the next decimal moles. Okay, that's whatever. Then that's the answer in terms of moles. Then the second part, what about the number of atoms? I will say that I know 1 mole is equals to 6.0 times 10 to the power 23 molecules of carbon dioxide. And then what about 6.5 grams? 6.5 grams. Note, I will avoid using, unless you don't have a choice, I avoid using the calculated volume, because you saw like here we approximated the answer was 14777 something, and it goes forward 7727 what 2727. And because we introduced an approximation here, which is approximation and error, when you come to calculating the next one, if you use the calculated figure, you propagate the error. You realize in your mathematics topic, approximation and error, anytime you approximate something, you introduce a small error in because of that approximation. So because of that, you want to use the original amount. So instead of me finding, I can use these moles to find the particles, but I'm better off using the original amount. So instead of the calculated amount. That's one, because of approximations. introduces some errors, and those errors you propagate them. The other thing is that if at all I did have a real arithmetic problem here, like I got the wrong answer, if I use my wrong answer from my calculation to calculate ahead, then I am in more problems. But when I use the 6.5 grams, I know that was the original figure, so I'm in my own hands, and therefore I'm pretty okay. So it's a 6.5. I'm looking at the weight of 6.5. Is it right? This is not right. Why is it not right? Why is it not right? It's not right. Allow me to cancel all of it. Formula is not okay so far. So I'll say, I will start again. I'll say 1 mole. Where is the brush? My pen, 1 mole is equals to 44 grams, and it contains 6.0 times 10 to the power 23. What about 6.5 grams? How many? We are not looking. Okay, it's saying atom. That's what we are going to find. So our answer will be 44x is equals to 6.5 times 6.0 times 10 to the power 23, divide by 44, divide by 44, and then we cancel it like that. And this we should give us, let's get our calculator down here. Let's get our calculator. 6.5 multiplied by 6 over 44 equals 0.886. 0.886 times 10 to the power 23. This one I can't leave it like this. We said this is 8.86 times 10 to the power minus 1 there, times 10 to the power 23. And this one becomes 8.86 times 10 to the power 22. These are molecules. Molecules of CO2. But the question is not asking that. The question is asking us the number of atoms. So what we'll do, this is a good one, because it will force us to do something extra, is to know that in one carbon atom, in one carbon dioxide atom, CO2 atom, I have one carbon, and 2 oxygens. Okay, so if I have 8.86 times 10 to the power 22 molecules of CO2, it means I have how many carbons? It's one carbon for one CO2. It will mean I have 8.86 times 10 to the power 22 atoms of carbon. But I know I have 2 oxygen atoms for each molecule of CO2. So it means I have 2 multiplied by 8.86 times 10 to the power 22 molecules are atoms of C, which will give me something like 8.86 multiplied by 2, 12, 17, 17. Then 1, 2 is there. 17. Where's the pen? It's 17.72. 17.72 times 10 to the power 22, which will be 1.772 times 10 to the power 23 atoms of O. Okay, and I think based on that one, excuse me, up to so far, I think we have covered quite a substantial amount. Do revisions on that one. Make sure you do lots of exercises. This is all about exercises. Get exam papers, do them, attempt them. You want get to perfect this one by exercises is like getting your muscles, getting to lose weight, getting to be acting the way you want. You only do it by putting up the work. And the only way you are going to achieve here is by doing the exercise. You can get it right here, but if you don't do your exercises, a lot of them, they will just disappear and you'll be back to where you started. Don't let your brain tell you what to do. You tell your brain what you want to do. Don't get tired. It's not the time to get tired. It's the time to put down the work so that you achieve what you need to achieve on that exam, so that you have a better chance going forward. So I'll leave this first lesson here so that you look out for the next lesson. And so where we continue now by looking at some more molecular modes of compounds. And from there, there is something to do with empirical formulas and the masses related to that, then molar gas volume, and continuing like that. Okay. Cheers.